Hi, Rahul.
Hello, Sudhir.
Thank you for joining.
Thank you so much.
Half a minute before Taruna introduces everybody and we start.
Sure.
Vijay, thanks a lot for coming so early in the morning. This is really
not a problem. Thank you.
Taruna, maybe you could start.
Yeah. Good evening, all of you. Myself, Dr. S. Taruna, feel very glad to introduce the panelist of this particular webinar. We have with us Professor Dheeraj Sanghi, Vice Chancellor of JKLU University, Professor Rahul Banerjee, Director LMNIT. We are very happy to have you with us, sir. We have Professor Sudhir Raniwala, Dean Faculty Affairs, JKLU University, Professor Amit Sinal, HOD CSE Department, Professor Devika Kataria, HOD of EEE Department. Now, without taking much of your time, I just hand over the session to Professor Sudhir Raniwala to introduce our guest.
Good evening, everybody. So while the Vijay's introduction has been circulated to everybody and put in social media, it is customary that I should talk about this for a moment. Dr. Vijay Saraswat is a computer and AI scientist, very well known for his work in logic, concurrency, and programming languages. Over a 35-year career, he has been a researcher at several of the world's iconic research centers, including Xerox's Palo Alto Research Center, AT&T, and IBM's T.J. Watson Research Center. Most recently, he was the global head of the AI R&D at Goldman Sachs. His current occupation is, with effect from 3 days ago, laying the premise of his own company, Language Machines. May the company grow to realize the dreams of its founder. And let me also make a personal comment. All my life, I must have met thousands of students and friends and collaborators. And yet, whenever I think of a person who has had the most diverse interest and as many competencies, the first name that always emerges is Vijay Saraswat. A school-time association with Vijay, being classmates, gives me enough pride to bask in reflected glory of his contributions and his achievements. Many thanks for accepting to talk to us, Vijay, on the dawn of the AI age, soon after the dawn at your place early in the morning. Over to you, Vijay.
Thank you so much, Sudhir. It's indeed an honor and a pleasure to be here, both amongst friends and back in a city that's effectively my hometown in India. And as well to talk about this topic. I've been, as Sudhir mentioned, I've been in computer science almost 40 plus years at this point. And these dreams of building powerful computers, powerful systems that are able to think like humans, reason like humans, communicate with humans using language. These have been around from the very beginning of the field. Back in the first workshop that led to the coining of the name artificial intelligence, John McCarthy spoke of an advice taker, a program that would actually take input from us in English and essentially be able to solve problems. For 60 years, 60 plus years, we have been working a large group of people, the large diversity of techniques to move forward these ideas. And really, it's in the last 3 years, I would say, that we have hit a a certain knee in a hockey stick curve. And we are now at a place where tremendous progress is being made. More or less every month, every week, there are new ideas on the table that promise to have a pretty significant influence. So my goal today is to give you some sense of perspective on these new developments, and particularly lay out what I think is a very stark contrast between how we have developed and practiced computer science for decades and this new set of developments that lead to what I'm now calling the first generation of computers for humans. So let's get into it. I have sent my slides to Sudhir. There are a bunch of references in these slides. So hopefully, if you have certain questions, you can follow up some of those references and see. And I will be available later, online if needed, to answer questions from people. Maybe not just today, but at some later point in time. Okay, let's get going. So a lot of the work in computer science, I would characterize as computer science 1.0, the first multiple decades. And roughly speaking, here is how this works. You've got some problem. You as the human, you as the programmer, think of a representation of the real world that is adequate for that particular problem. You must have in mind algorithms, procedures that when executed will accomplish the task that you are trying to solve. And so your job is to write in an appropriate programming language these procedures, these algorithms in such a way that now they can execute on your digital computer, which has this amazing capability of executing billions of instructions in a second. And you have this ability to work at scale with a tremendous amount of data, your memory available to you. Used to be kilobytes, now we are talking gigabytes of memory. So immense amount of resources available to you in this enterprise where you, the human programmer, are in this situation where you have to conceptualize the task, the representation of the world, figure out how to make that available within a computer using the abstractions that are given to you by the computer, starting out with floats and bits and floats and integers and strings, and then using your programming language abstractions, you build up more and more sophisticated data structures, but it's your task to render it all in computation, render it all in code. And we've made tons of progress. More recently, in the last 20 years or so, there's been a lot of progress in getting to what Armando and other colleagues have developed in this thing called sketching, where you don't provide a complete program. Instead, you provide a program with holes in it. And it's the job of other tools to flesh out the code that should live in those holes so that the overall program can be developed and executed. And at some level, the connection between 1.0 and what I'm about to talk to you goes in my head through this idea of sketching, where we are looking to get the underlying computational systems to do more and more of the work of realizing these programs that otherwise we are writing manually today. So let's get to the situation. So get to how does computer science 2.0 begin? When I say 1.0, 2.0, I'm not necessarily implying that when you start working in a 2.0 context, 1.0 is irrelevant. We will still need those ideas. But 2.0 really represents a significant departure from the way 1.0 was being done. And that's the main point. So the central issue is, what if you don't actually know how to write that code? What if you don't have an algorithm that you can simply translate into instructions for this machine? Now, you would ask, why would we even think of a problem like this? Well, because the world is rich with problems. We are, in fact, in many cases, we have at hand other sources of information. We have at hand data. So let's look at this problem. We've got images. And what we wish to do is we wish to find some way of labeling those images with pieces of text that succinctly characterize what is going on in those images. So, on the top left, you'll say you'll say, oh, that's people. There's a child, there's a house, there's a study, things like this. Now, if you ask me today to write a piece of code to do this, in the old style, it's very difficult. How the heck am I going to do it? We are talking of a range of inputs that could be essentially any image whatsoever taken on this planet. So very large diversity of input, very high dimensional input, meaning there are a tremendous number of components within this input that need to be understood. You know, the different pixels, the colors of those pixels, depth, lighting. There's so many different variables that can affect what it is that is in that image. And somehow we've got to figure out the algorithm that will allow us to produce succinct labels of the kind that you see here. So I don't know how to write the code. What else do I have access to? I do have access to data. So here, and this is one of the remarkable secrets of this modern world, it depends a whole lot upon getting high quality data to start with. Here, Professor Fei-Fei Li from Stanford is credited by some of the leaders in the modern deep learning work as being the person who actually spearheaded the work that led to about 50,000-60,000 images being labeled in this way. And that provided the essential power that was needed for these new techniques to work. So where are we? We are in a situation, we've got lots of data, and we will say that the data is labeled. That means we've got some input. In this case, the input is going to be an image, and we have an associated output for this, which is going to be the label for that particular image. And let's say we have plentiful data, 60,000 elements. We don't know the code for this agent that lives in the middle. Is there some way for us to figure out that code using other computational techniques? And that is effectively the space of machine learning. The ideas in this space are actually fairly simple at some level, though, for people who grew up in the old school way of doing things, logic-based, discrete computer science, these are quite new, and you have to get your head wrapped around it. The underlying mathematics is very different. You've moved into a space where what you have available to you are continuous functions. Because what we're going to do now is this. We are going to go figure out, get our code to learn the representation of this function. So there's a function that we have in mind. It's in our heads, the labeling function. We don't actually have the code for it, but we think that we can get an approximation of that function. So now we need to go figure out what is a space in which the different possible realizations of this function live, and which of them are good approximations to what we want, and then how do we select automatically that good approximation from the space of all of these approximations. So as usual, these things that are successes overnight have had decades of work going into it. This concept of neural networks was being worked on. The basic algorithm for gradient descent, the so-called backprop algorithm, was developed way back in 1986 or so. But those techniques were at that time, I was a graduate student, Jeff Hinton was at CMU teaching courses on neural networks. There were other colleague graduate students of mine working on Boltzmann machine different architectures at that point. But for us guys coming from the logic view of the world, that seemed like an outlying area. It seemed like these underlying ideas that they had were quite interesting conceptually. This idea that the kind of discrete representations of the real world that we do in logic and how we write our inference algorithms in a production system language like ops or in logic, according to Hinton and colleagues, those ideas were just wrong. And they were wrong because it wasn't at all clear how to use data from the world to get a system to automatically learn those representations. And their insight was that this alternate technique, where what you are working with is these very high parameter count, large networks, where what is in this network? You see here, what you've got are utterly simple compute elements. A compute element, one of these elements, a neuron, so to speak, is connected up to the outputs of other such neurons in previous layers. And what you have is that this little system, all that it is doing is it has a collection of numbers called weights. It's taking a weighted combination of its input, producing an output, and then applying, crucially, something called a nonlinearity on top of this output. And a nonlinearity need not be something very complicated to get your head wrapped around. It's something like this. You've got an input. If the input is negative, your output is going to be 0. But as soon as the input is positive, your output is just going to track your input. So it's a nonlinear function. It's actually, we've got a discrete jump at it. You can have smooth approximations. You need some kind of nonlinearity in the way this whole thing is set up. But now this is what I want you to start thinking of. Your computer, your little function approximation that is going to get built up, in fact, has inside it literally hundreds of thousands of these small computing elements arranged in some kind of an architecture. The output of some is going to the input of another. Maybe there are layers, and the output of the neurons in one layer goes to the input of the neurons in the next layer, and so on. Ultimately, at the top, you're going to get back an output that you will then interpret in the way that you wish. In our case, we want to interpret it as a piece of text. So crucially here, we are working all in the space of what I said, continuous functions. So essentially vectors of floats. Your input is going to get translated through some scheme that I don't have much time to talk about, but let us imagine you've taken a sequence of text, or in this case, an image, and you figured out some way to chop it up into pieces. In the case of text, those pieces would be called tokens. Those are parts of words. And you have some way of starting with those words, those tokens, and getting a vector. That's called an embedding for that token. So this whole stuff starts out with, you've now got a vector for each one of these tokens. You've got a piece of text. You've got a vector for each of these. Feed that into the system. That system will have weights. The crucial point is, where the heck did these weights come from? I'll get to that in a second. This system has weights at these different points. Take your input, multiply with the weights, produce the output, keep doing it till you get out, apply a nonlinearity till you get out at the end. That's your answer. So the real question to ask when somebody comes to you and says, hey, this is how we are going to reconceptualize all of computing is, okay, are these things that you have, these candidates for function approximation, are they universal? Can any function in the space that is of interest to me be represented in such a way with some choice of weights? And the answer to that was very early on. It was clear that that answer is yes. But it turns out that one of the big insights that was driving folks here, Jeff Hinton and Jan LeCun and Yoshia Bengio, the folks on whose shoulders all of this work has been built up, the central insight that they had was, hey, it's not just that you want to be able to represent any function. You want to be able to represent it efficiently with a smallish amount of data. Even now we're talking, large amounts of data, but you want to be able to learn these things efficiently. And their intuition was, you do that well when you are in a setting where you've got a large number of layers. And that's the beginning of this idea of a deep learning network or a deep neural network. Deep is in the sense of the number of stacks in this network are large, let's say hundreds of layers potentially in the systems that we are working with today. There are actually hundreds of layers. So the thinking was that if you are able to structure things in that way, you will actually find, and here's an example from an image, that the initial layers are picking up some local structure in the image, in this case, things like edges, and then the layers above that, again, you have to structure your architecture correctly for all this to happen. They are picking up bigger patterns on top of this initial input structure, ultimately getting to patterns that are close to what, in this case, let us say this is a face database of faces, how a human would look at that kind of input. So this successive building up of a representation of real world phenomena automatically by the system, this is a key characteristic of this kind of 2.0 representations. Now, of course, the central question is, how does this happen? We've got, and potentially here we are talking about networks that may have thousands of parameters, hundreds of thousands of parameters, billions of parameters. In fact, it is said that GPT-4, the system that we are going to talk about mainly today, has 1 trillion parameters. So an absolutely immense number of parameters. Where do these values come from? And this is the other part, the other shoe, so to speak. There is, in fact, a single algorithm, so-called stochastic gradient descent algorithm, that is actually adequate to work on this immense amount of data, to work with very large such networks and learn those parameters in a way that is faithful to the data that you have provided. So again, you've got lots of data, you've got an input, you've got output labeled data. You are going to now learn from the space of all possible values for these parameters, those values for the parameters that adequately deal with the particular data set, the 60,000 elements given to you. In that, given an input in the 60,000 data set, you will get the output that this thing wants. So you're fitting your function to these data points. But of course, you don't want to fit it just to these data points. You want the function to be abstracting away regularities in the real world. So if you were to give it another image, something it has never seen before, it is able to produce an output that is consistent with all the data that it has actually seen, but in fact, it may never have produced that output before. So we are looking for these networks to appropriately generalize. This is the essence of machine learning. Finite data set, infinite function, that's what you want to learn. How does generalization happen? So there's a whole lot of theory here about how you want to structure your network so that you do get adequate generalization. There is this whole hypothesis, the manifold hypothesis about, in the real world, there's actually a lot of implicit structure. It's not just random stuff. And that implicit structure is what we are looking to get our systems to understand. But all of this works only because we have a technique for trying to find those weights. And that technique, in some sense, is very simple to describe. You might have, I'm talking to the students here, you might have, in fact, already done things like find the minima of a function, like some kind of a polynomial function. And you know the trick there, you find a point on the curve, and then you look for the point of steepest descent. And then you take a small step in that direction and update until you find a point on the curve that is close to the point that you get when you take a single small step in that direction. Keep doing it. You will smoothly descend until you find the minimum. And now you can stop. You found your minimum. That works great in convex spaces. The amazing thing about stochastic gradient descent is that people were able to start with that simple intuition and make it work in very high dimensional spaces and with functions that are not necessarily convex. So that's the sort of technical achievement here on how you make this whole thing work. You make it work because you've got this powerful algorithm that knows how to do this kind of gradient descent in very complicated spaces. Use that algorithm. If you've got the right data, you've got the right architecture, then you'll find that you're actually able to learn these weights and not turn around and use that in a real setting. I have a bunch of references here for getting to a lot more detail. It is completely not obvious that this would actually work. And in fact, I would say the decades that were spent from this initial discovery, the decades that were spent were really spent trying to understand this problem better, fine-tune the way that stochastic gradient descent works, realize that scale is what matters, and so on. This is the essence of what is going on. It's a beautiful little 8-paragraph a blog by Rich Sutton, where he captures what he titles it the bitter lesson. And this is really telling us, why is it that these new techniques work? And the central point is this: the old way that we did AI, that I did when I was at Park, I built out, systems, large logic-based models for copiers, complex electromechanical systems with computational control, really interesting challenge. So we built it out. We studied the problem. We figured out what sort of logic we want. We made that representation for discrete and continuous control, change, all of that stuff we did. But the point that Rich is saying is that that's just wrong. And that's wrong because ultimately all the major breakthroughs, it's an empirical point, all the major breakthroughs in AI have not come by very smart people figuring out the logic in a particular situation. They have come from general techniques that leverage computation. And this is the central point of the stochastic gradient descent algorithm that I showed you. That's an algorithm that works for 1,000 parameters all the way up to 1 trillion parameters. That is scaling. That ability to bring computation to bear to unearth patterns in a vast amount of data by using a single algorithm, that enables our code to do things that humans don't work in that way, in a problem solving in that way. It's very difficult for humans to do that kind of thing. So the bitter lesson is, it's not for us as researchers to figure out a problem and then write its code out in the old 1.0 style. It is for us to figure out the architectures which will then figure out those representations which are adequate for dealing with the full complexity of this real world problem that has noise, that has high dimension, that has uncertainty, and so on. So I really recommend people take a look at this. Now, this is in essence what we are seeing now. So let me get to my next point. These ideas of we are going to learn an approximation to some function, and we are going to throw a massive amount of data, and we are going to learn using this single algorithm, stochastic gradient descent. That is at the heart of the development of large language models that you see in the GPT-4-like setting. So in some ways, the general problem of reasoning, representing and reasoning about the world, the central problem of AI accomplishing tasks in the world, you now see a path to that through this idea of, let us actually figure out how we can get such systems to understand language. So in some sense, this is language as the wormhole to AI. That's what we are seeing now with the discovery in the last few years. Before I go there, I want to point out very quickly some of the amazing advances going on today in what is being called generative AI. The language part is what I'm going to focus on mostly today. That's only one part of it. There's also amazing stuff going on with other media. Again, in the real world, it's not just text that we use, images, video. These are all part of what we use to communicate with other humans. It would be fantastic to get our code to understand these other kinds of media as well. And indeed, you, I'm sure, are very familiar with the fact that in the last 6 months or so, there's been tremendous progress in the automatic generation of images which satisfy certain conditions here. You know, I just went to Dream Studio just before this talk and wrote out a little prompt in English, these few words, ask the system, hit the dream button, and there you get these images. I asked for some abandoned temple in Amer outside Jaipur in dry desert-like conditions, and it went off and it produced something that looks fairly realistic. You can imagine the immense power of this kind of text modulated generation of images in all our creative stuff, in advertising, in entertainment, in movie making, and so on. But unfortunately, I don't have time to talk about all this. I want to focus on language because the story of language itself is amazing. So let's get to it. This, in some sense, captures my take on the essence of what is going on with large language models, the 5 pillars on which this stuff stands. So the neural network architecture I talked about before, I just gave you the simple abstraction. We got simple compute elements. We need layers of those things. Obviously, in order to deal with the complexity of tasks that we wish to learn, there's a lot more sophistication going on. And it took several years for people to realize that there is something called a transformer architecture. The paper came out in 2017, which the central problem you have to deal with here is with language. You've got sequencing. So you're going to take as input some piece of text, and it could well be that the meaning of this piece of text depends upon interactions between the first element, or an element, a token, a word at the very beginning, and a word at the very end. This is what makes language so interesting and so complex and so rich. compact ways of representing lots of information about the real world, but you will have all of these interactions. So the central challenge was to figure out what kind of neural architecture can we design, which allows for these long-range dependencies to work out. The system should be able to learn about these long-range dependencies. That was the question, but what should that architecture be? Before this, people were dealing with some linear architectures like a long short-term memory, LSTM. There, the idea conceptually, I would say, was very simple. You have a state, and that state you are threading through like a finite state machine. You got a piece of state, you got one input, you marry the input to the state, you will get a new state, possibly an output. Keep doing this, and so until you get to the very end. The big challenge is all the interaction between the first word and the last word is mediated through this one channel, through this single state. And that can be very narrow and simply not adequate to deal with the full complexity of language. The idea behind this transformer architecture is we will directly represent the pairwise interactions between elements in the input. So you now pay the cost of a square interaction. At every point in this grid, there are learnable parameters that will learn the value as you flow all your data through, but you're now permitting the possibility of direct interaction between any two elements in your input sequence. And of course, you do this in a layered way, so that in the first layer, you build up a representation. Second layer, you repeat this very thing. Third layer, repeat this thing. So now you've built up an architecture which has the potential to learn very deep, complex patterns out of data. We already have the algorithm which will allow us to learn it. So flow that algorithm, flow the data through using this algorithm on top of transformer architectures. That's the heart of all the things that you are seeing happen in deep learning for text today. But the big question to answer is, fine, where is my data going to come from for text? I showed you labeled data first, input and then an image, image as input and then a label. And Feifei Li did heroic work with her students and others to get those 60,000 labels done. But the level that we are talking about, where we want to take as input all of the text on the internet, trillions of tokens, we simply are not going to be able to organize humans at the scale needed to be able to label those things. So now we turn to a new idea called self-supervision, which is essentially just give me text. The amazing thing about text as it occurs, even on the internet, is it's far away from random strings. Randomness is there are a lot more random strings than there are strings that humans produce. So implicitly, there's a lot of structure in language that comes about simply because we are able to say, hey, that's a random string, or this is a piece of language. This is a human-generated string. So how do you make this real? Here is the way to make it real, something called a language model. And that underlies, of course, these large language model ideas that you, names that you see around. So what's a language model? A language model is very simple. Given it, the problem is this: I'll give you a piece of text and I want you to figure out what is the next token in this piece of text. Cat on the hot tin. How do I complete this? Well, okay. And what you want is a probability distribution on the next token that comes in. So you can have all of the tokens in your vocabulary, say 50,000 tokens. And if you have learned on your language properly, you will find on all the data available to you properly, you will find that things like roof are likely to have a high probability. Other tokens are likely to have very, very low probability. So now we set this as the task. The task is for a neural network to simply learn the probability of the next token given a previous sequence of tokens. Now, where do our labels come from? That's easy. I already have a sentence. I start out with the cat on the hot tin roof. I give my input to the network as the cat on the hot tin blank. I have the answer roof already. When I send it through my network, it's going to produce some token as output. I take that token, I compare it with roof, the one that I already had. And now if they're the same, fantastic, my network has learned this. If they're not the same, then I compute the difference between these, what's called the loss. And that's what I propagate back through using stochastic gradient descent through my network. The main point is I now have billions of labeled data points. All I did was use a simple algorithmic idea to start with my unlabeled data, generate a label from it. And of course, it's not an arbitrary thing I'm trying to do. There's a deep intuition here that the structure of language can be recovered merely by being able to extremely well predict the next token. So your network, in having to learn how to predict the next token over trillions of sentences, will actually learn something about the real world that these sentences are about. This is the insight on which all of this stuff is built. So we start with so-called causal language model. That's the task we set our system to. And then here comes another important insight. I gave you before a picture where we are learning an approximation function for a specific task. The task is, hey, predict the label for an image. But really, we want to be able to give our computer all sorts of problems and have it produce answers for that. So if I have to train a single network for each task, there are hundreds of thousands of tasks. This is going to be very difficult to manage. So another insight is, let's actually leverage the power of language to do this. So you'll have one single task, not hundreds of thousands of tasks. That single task is you take as input a piece of text, and you produce a piece of text that will follow using these language model ideas. That follows is a natural continuation of that piece of text. So that's the single task. And guess what? You can take all sorts of real world problems that are very different from each other and represent them in this way. Your task is to translate English to German on an input that is good. Excellent. That's the piece of text you give to your system. Translate English to German. That is good. You specify the task that you want in text in the input. So one task where it's taking one task for your neural network that's taking the actual thing that you want to do as input. And you've got your data on which you wish it to operate, and it goes off and produces the desired output. Summarization, finding sentiments, extracting information from documents, all of that stuff can be expressed in this way as a piece of input from which you're going to produce output. Okay, and then we already discussed this, Rich Sutton's point, scale. Use this transformer architecture and use a large amount of data available to you and build out bigger and bigger networks. In some sense, the magic moment in the large language model space happened in 2020, January or so, when GPT-3 came out. They were the guys who made this big jump all the way from 13 billion parameters to 175 billion parameters. And they were guided by their intuition that scale will get us interesting results. And indeed, they were right. We saw with GPT-3 that opened the eyes of so many researchers. We saw phenomena. We saw the system doing things. For example, being able to match patterns that do complex pattern matching on problems that we just came up with. On the spot, you come up with a completely new pattern matching problem. You give it a couple of examples in text, and it is able to figure out the general rule and apply it on a new example. And you have no reason to believe that it's ever seen this problem that you are giving it before. So this so-called in-context learning was the first time that we saw this phenomena with GPT-3. GPT-4 today, ChatGPT that came out back in November, is a version of GPT-3 with this thing that I'm calling, that is being called RLHF. I'll come to that in a second. But it's still more GPT-3-like. GPT-4, there are no details out about its construction and so on. But I'm told by reliable sources that, in fact, it is a 1 trillion parameter network. So it's significantly bigger than 3. And what we do see in behavior as we use the system is that GPT-4 is far more powerful than GPT-3 and GPT-3.5. There's one other idea that will close out these pillars that's important to understand. And that's this problem that actually it would have been fantastic if all the tasks we wanted to do could be obtained merely by completing a sentence, as I talked about before, the given passage. It turns out that if you just do that, the system, it's very easy for it to go off the rails and start producing things that are not helpful, that don't actually get your task accomplished. Again, what we're really trying to do is we are trying to build a new computer, a computer where the instructions that we want the computer to execute are specified in English, like so. Like translate English to German, that sort of thing. So we want the system to be essentially executing the task that we are giving it. And so this idea of reinforcement learning with human feedback has been the critical idea that OpenAI in particular has developed, which has allowed ChatGPT to be significantly better than GPT-3 and has allowed GPT-4 to be significantly better than ChatGPT. And this idea is, so far I talked about there were no labels. We generated those labels, self-supervision. This idea is we are actually going to use preferences from humans. So we are going to go back and get some more labels from humans on the input task. You give it the input task, you ask the system to produce, these are non-deterministic, there's probabilities there, so it can produce many different kinds of answers as you tweak your probabilities. So sample 2 answers, and now ask the human to say which answer is preferred by the human. It's very difficult to get humans to agree on complicated tasks on what the real answer should be. And here you need a lot of humans to work on it because you need a lot of data. So instead you ask a much simpler question. Don't tell me what the answer is, but just tell me these 2 things that I am giving you, which one is better? Give me that preference information. And then using that preference information, it turns out there is another branch of machine learning called reinforcement learning that can be used to learn much better technique in this neural network for continuing your sentence and getting good results. So these are the 5 things that taken together underlie the behavior that you see with GPT-4. There's been so much, I mean, I'd like to tell people it's actually, just look at demographics, it's pretty stunning. 80% of all people who have ever lived who were scientists are actually alive today. That's just the nature of exponential growth, in this case of population. And of course, it seems to me that 80% of all the scientists who are alive today are working in deep neural networks. There's just so much work going on in this space. Here in the last 2 years, you see so many large language models having come out built on the spectacular success of GPT-1, GPT-2, and GPT-3. So it's tremendous work. So now let's take a look at what is it that GPT-4 can do. If you go look at the GPT-4 technical, well, it was more a marketing brief that came out. A very interesting thing in there is results on tests. So back when I was at IBM Research, we had actually proposed back in 2015, 2016, that clearing, the CPA examination, getting a piece of code to clear the CPA examination would be a grand challenge. We should work on that. Well, guess what? Now we are in a situation with this one piece of code is able to do extremely well on a large variety of these tasks, these tests that were set up for humans, for SAT, college clearing, graduate entrance exams, and so on. The full things are on that in that paper, so please take a look at that. The full set of results, these are much better than the results for previous pieces of code. But now, in some sense, I can say that the task that many of us are engaged in is actually to understand this. What is it that GPT-4 can actually do in the form of understanding language, in the form of answering questions? So I am actually now going to show you a few of these examples. But before I get to that, let me summarize this whole part by simply saying this is where we are today. We finally have, so far in terms of information processing, you had 2 kinds of systems. You had the 1.0 computer science systems, these digital computers, where you sit and write the algorithm. And that's how you specify what you need done. Then you have humans. You can talk to your colleague and explain to them in language what is it that you'd like done. And if they feel like working with you, they would probably end up understanding problems the way that you want it to, and they can go off and execute. For the first time, you've got systems that have characteristics of both. These are not human-like. A GPT-4 does not really reason. There are lots of people making claims otherwise, but it's very hard to actually see a GPT-4 as a kind of a human, because the kinds of mistakes it makes, the kinds of generalizations it makes, they have their own unique flavor. We have, the way to understand it is that we have this algorithm I mentioned, stochastic gradient descent. We have all of this data. We have the loss function that we provide. Out of that emerges some complicated behavior. It's human-like in the sense that it's taking as text input, but it's like a digital, old-style digital computer because it's actually been trained on all the text out there. No human has been trained on all the text out on the internet. That level of scale, and of course, these systems use way more power than humans do. So computational characteristics, information processing characteristics are very different for these large language model-based machines than they are for humans. We must keep that in mind as we analyze these systems. But importantly, this is where we are now. We have the first generation of computers that humans can use by interacting in the way that I will describe in more detail shortly. And importantly, they have access to all the language that we as humans do. If I'm on the intranet, all my company private documents, those can be fed into a language model, and a language model can be trained on these things. And now this stuff can answer my questions about my company's proprietary information in a way that we simply never had systems like this before. Let's take a look. What sort of things? This is a kind of a problem which is very astonishing to see GPT-4 deal with it. This is reasoning about the physical world. In AI, we've had this group, people who care about reasoning about the physical world for 40 years or so. And we've never been able to come close to a program that could answer a range of questions about physical reasoning like this can. I'm standing facing north. If I turn right through 90 degrees, then I lie on my back, then I turn on my right side. Which direction am I looking? Okay. And here we can, this is straight given to GPT-4. You see not only the answer, but you see the sequence of steps that it goes through to reason and get to that answer. Then Millikan's, Sudhir, you will love this. Simple example of again, these are just taken from things that previous systems had great difficulty reasoning about. You got Millikan's oil drop experiment. You are suspending an oil drop between two charged plates. And the idea is to counterbalance the weight of that oil drop by the electrostatic force between these things. And I'm simply asking my system with the right, this is a description of my experiment. I'm asking it a question. Please choose between A, B, C, D, and E. How should I charge the plates? And it comes back and it reasons and it actually gets it wrong. So here is another big thing you can do with GPT-4. You can actually correct it. So in this case, I'm simply asking, please check your answer. And it comes back and it's got this ability to actually review what it has done and come back with, in this case, a changed answer, which in this case was the right answer. So this is actually pretty interesting. You can also ask it things like, is it possible to fold a guava? Previous systems had great difficulty with this sort of question. Yes, impossible questions. Is it possible to get a boiled egg inside a watermelon without cutting or breaking the watermelon and keeping the eggshell intact? Now, this is an impossible situation, but you want to keep properties of the real world alive as you reason through this stuff. You don't want eggs to suddenly mean, a gas cloud. It still should be an egg that has a discrete content. Again, this system is able to reason about this in a way that is quite plausible, and so on. But, and here is one more thing I will tell you. You can ask the system, it's just text to text. The big challenge is to figure out what text you want to give it as input. Here, the text I gave it as input was, okay, I'm coming up with all of these examples, which I'm trying to test the system. Are you good at it or not? Why don't I ask the system to produce for me problems that it thinks it is going to have difficulty with? That's the beauty about language. You can start using language in all sorts of reflective ways. Do that, it comes back with some very interesting examples that it does have difficulty with. So I'm not going anywhere close to saying the system understands itself, because I don't think it does. I'm saying that the complex patterns that are built up in this system through the techniques that I've described are such that you can get such very interesting results on a wide diversity of topics. Always ask GPT to check its answer. Name the first ever animated feature film. It comes back. So now there are two things going on. There is knowledge inside the system of the real world. And then the system, I mean GPT-4, has the ability to reason about these things. So the knowledge about the real world I'm asking it is, name the first ever animated feature film. Comes back with Snow White. Just whenever you use GPT-4, use this little trick. Every time it comes back with an answer, ask it, are you sure? If so, say yes, or QED, or pick up some token that you care about. If you're wrong, correct your answer. I'm really giving it no new information about the problem. Just asking it, please check. Now, of course, you would say, why doesn't it check on its own? Well, it doesn't, because we don't have these very crisp ways of training it. We just train it like I showed you on all of this data. What it is learning, very hard for us to control what it is learning. But now through language, we can get it to do things like, I ask it this, it comes back, says, oh, I'm sorry. I actually had another answer. This is the answer. Of course, I know this is the right answer, but I need the system to be confident that this is the right answer. Just ask again. Keep asking in a loop until you cross a number of levels, or it comes back with a yes answer. And it says here, yes, I'm sure, and so on. So this kind of auto-correction capability, we never dreamt that a system trained in this way would somehow get it. And that's what I mean when I say that our new challenge is to actually figure out systems like this. What are they capable of by figuring out the right inputs to ask and getting the right output? I don't have a lot more time, and I have a lot more slides. You will have my slides, so I'm just going to show you very, very quickly the kinds of things that this one program can do. Give it a complicated piece of business text. In this case, I work in finance. In this case, it's a financial instrument that actually has, it's surprising how much in finance people use mathematics constraints. Lawyers writing really Python in text. And you are going to develop a model for this financial note. So you need to recover that piece of logic. And I ask it to produce for me this formula that describes payment at maturity and give it to me as prologue. Yep, I get that answer. And it gives me an explanation of this. Look at this. This is fairly complicated stuff. I gave it more text than just the text that contained the formula. And it is able to focus in on just the piece of information necessary to pull out that right formula. Tons of examples of this kind. There's a recent major judgment in India around, so I'm talking now of legal analysis around, antitrust case involving Google, complicated, summarization of the case here. I asked it, please summarize. Here's the account, please summarize. And it gave me back 3 paragraphs, which I showed to lawyer friends of mine. And, that's a pretty reasonable summary. And imagine this can be done today by every lawyer in India, USA, wherever. We have the system available at scale to be used by all sorts of professionals. That's not it. You can turn around and ask it, give me the structure of argumentation in this judgment. So it gives you the 5 arguments that were made. Then you ask it, give me reasoning that I can use in the next court to actually try to overturn this judgment. And it gives you some reasonable answers there. Again, not necessarily what a professional would give you that you pay tons of money for, but a good start for these sorts of things. All right, I am going to skip. I want to quickly touch on this. It turns out that GPT-4 is actually trained on a modest amount, on a huge amount of English, a modest amount of other languages. And it does show very interesting capabilities, multilingual capabilities. Here, I just gave it the Gayatri Mantra, said translate into English, and it gave me the version of it in English, and then a description, which is actually pretty reasonable. I ask it, give me, Kamaini. And it gives me a description in Hindi of this stuff. I'm asking in English, it's responding in Hindi. That's okay. Again, understand that the underlying network is really dealing with a sequence of tokens. I never said that those tokens need to come from a single language. In fact, the system has been trained on not just text in English, it's been trained on code. The reason it's able to produce so much interesting code is because its training set includes a huge amount of programming language code. And you can train the same single system in Bengali, Tamil, English, Hindi, and so on. And that's how you get these sort of multilingual capabilities coming out. I asked a friend of mine, I don't know Tamil, I asked a friend of mine who is a native speaker to converse with it and give me some examples. So he gave me some examples, pointing out that it's not very smooth. The question I had in my head was, hey, is this already as good in Hindi and Tamil as it is in English? And the answer seems to be no, not really. Some of the things that we saw earlier when we were working with smaller models, it's not very fluent. That kind of thing you see when you're working in these other languages than English. So there is work to do here to get it to be much better in terms of this stuff. Quickly,
Vijay, I hate to interrupt you. Sorry, Vijay, I hate to interrupt you, but maybe it's a good time to wind up so that we can actually have some 5 minutes for interaction.
Absolutely. Okay. Let me get to my end slide. The future that I see is a future in which, in fact, we use these language models at the heart of our information processing architecture within the context of an enterprise. We're connecting up to relational databases. We're connecting up to knowledge bases, knowledge graphs, all sorts of things like this. And most humans, professionals, are now interacting with our systems in English the way that I have talked about it so far. And this is a big future that, of course, needs a lot more work. But this is how I see a dramatic change in the way that our enterprises work today, in the way that computers are used in enterprises today. There are a ton of issues. This is not all clear and simple the way that I have mostly portrayed it in this talk. These LLMs will produce wrong answers with great confidence. And so it's really critical for the humans working with it to understand that they need to look at this output and verify that this is right, or set up conditions in such a way that hallucination is minimized, and it is possible to do that. So there's a lot of work there. There's a lot of work to understand, intellectual. So a bunch of legal questions have arisen. Now there are a number of governments all over the world. They're looking very seriously at issues about how do we regulate this kind of thing. It's fundamentally where we are now is that we've got these powerful language processors that can produce stuff which is not necessarily aligned with truth and what the real world is. So the potential for mischief in the hands of bad actors, so to speak, is absolutely tremendous. So yeah, lots of progress has been made. There is still, from an AI point of view, huge amounts of progress to still be done. This is a slide from 7 years ago. These outer circles are essentially untouched. We are seeing amazing progress in analyzing legal stuff, but things like developing mathematics, getting the code to figure out which are the right questions to ask. These are very tough questions. All right. Thank you, Sudhir.
Thank you so much, Vijay. It was absolutely wonderful for somebody like me who could comprehend most of it, I would say, what you're trying to convey. Thank you so much, Vijay. There are a few questions, so can we actually look at those questions?
Please.
There is one question by one of our colleagues, Kshitij. He says, I find your talk biased towards GPT kind of architectures. Yeah. And you can read the question.
Oh, sorry. No, go ahead, please, if you would read it aloud.
No, and that makes me a bit sad. I believe it at least deserved a mention. I see no mention of BERT here, but which I suspect may be part of GPT-4. After all, it was the first architecture to beat many state-of-the-art models on different tasks.
If you remove, I wish to know. Okay, find your talk. But of course, folks, right? Look, I have 50 minutes, right? So, and in fact, in that one slide that I gave you, which shows the encoder-only architecture, decoder-only architecture, encoder-decoder architectures, most of my work is actually, my personal work is in encoder-decoder architectures, not the decoder-only GPT. But that's a level of detail that I simply was not able to find time to adequately address in this. So Bert was powerful, of course. Before GPT really took off the scaling, we used Bert for all sorts of, Bert is an encoder-only architecture, used for all sorts of tasks like classification. But again, remember, the big deal here is text to text. I can take not just a single task like classification and get Bert to run on it. I can actually take my system and run it on thousands of tasks. That level, that insight, really comes from saying we want to build a system that can produce very coherent output for all sorts of inputs. That's the decoder-only architectures that have that. And encoder-decoder, the T0 guys, the T5 guys have this as well. But encoder-only doesn't work so well when you're trying to generate huge amounts of coherent text. Okay.
Okay, there's another question. How can artificial intelligence potentially contribute to solving the Millennium Prize problem in math? And what is the expected timeline for AI to provide a solution?
I don't know. These are so hard. If you'd asked me, in fact, people did ask me back in 2015, no one could predict that in 2020, we would get this dramatic change. You have a huge amount of people working now with increasingly powerful techniques. We can now expect to see more breakthroughs happen. But which breakthrough when? I mean, you can't predict this sort of stuff. So I don't know. This math question you're asking is a very tough question. I would love to see a lot more work on it. And there is work at IBM and other places on getting real mathematical reasoning going, on integrating such neural network-based learners with actual constraint solvers and reasoners. But whether we will get to see a GPT-like moment there in the next 2 years, I don't know. It's very hard to predict that.
But with the time inhibited it, but somebody has asked this question, what are some of the ethical considerations to keep in mind when using language models like ChatGPT for interactive conversations?
Yeah, so what I said before is a loss of let me put it like this. Even if you're using GPT, you are still responsible for what you are communicating to others. So if so you are responsible for figuring out whether the answer that you're getting actually makes sense. Is it the right answer? And then that communication now is your responsibility. It is very easy for this to produce bad answers or wrong answers or incorrect answers. So you really must know what you're working or doing so far. Now, again, a lot of research going on how we can improve that, how we can get the system to be much more grounded in reality. Hopefully, we will see systems that are much better from this point of view. So this notion of whether you are lying or you're not lying or hallucination and so on, it's a pretty central thing to this whole approach that has to be looked at very carefully.
And our panelists are asking is something similar coming up from image data called visual prompting for computer vision?
Exactly. So there's a lot of, so this multimodal stuff, actually GPT-4 is supposed to have, and by the way, Kshitij, another answer is GPT-4 is a release system. PALM is another example of a large system, 540 billion parameter large language model at Google that was not released. There was a major step that was taken first by Stability AI and then by OpenAI to say, hey, these enormously powerful systems, we're actually going to release them for normal people to start using. Controversial step. Many say you should not have done it. This could easily be misused. But that's why I focus so much on GPT-4, because it's actually an available system that I can do something with. Now, I can do my own experimentation and form my own theories about what is going on. Now, I don't have access to its innards, so I can't actually do experimentation in the way that I want. So it's not ideal yet, but it is in a place that I can speak a whole lot more. Now Bard is coming out with PALM built inside it, so we'll have a lot more experience with Bard. The initial experimentations that people have done close to me are that Bard is not showing anywhere near the kind of performance that GPT-4 does on this large variety of tasks. So that was a reason for doing this. Now, coming back to images, GPT-4 also has, we are told, been trained on images. So simultaneously, and they've got some examples in their paper that talk about reasoning visually. You've got, some picture of a contraption that is put together wrong, and you want to ask the system to tell you what is the right configuration. It's amazing stuff. In some sense, language, the ability to reason in language, that's the core competence that a GPT-4 has, can be applied to images, can be applied to video, and so on. As we move forward, we will see a lot more of this integration happening, where these things become better at generating images, better at analyzing problems in images, at reasoning with images, and of course, video in due course. So not yet, but this is what people are working on. We should see great results very soon.
So there's one last question before we close this, and this is necessary so that I don't have to cook food after reaching home. Rashmi sent in this as a private message. Will the 5 pillars of large language models work on ancient languages like the Indus Valley script?
Absolutely. So this is a really important point. In some sense, there's been a lot of work that says, hey, DARPA and others focused on these so-called low resource languages. We don't have a huge amount of text, but we want to make sense in those languages. We want to make sense. What do we do? And I think the answer that we are beginning to see here is that if you have a system that's trained on a massive amount of text in a particular language, the ability to get it to understand text in a different language with some amount of training is improved than if you don't train it on a massive amount of some language. Again, at some level, what you're I think taking advantage of is the fact that we live in the, it's a very, very broad statement. We live in the same world. The world's regularities are expressed in language in different ways, even if it's a different language, but those regularities are the same. So if you've learned stuff in one language, you should be in a position to see that transferred to other low resource languages. So I think there is great hope for these large language model based techniques for extremely low resource languages as well.
Thank you so much, Vijay. I think we'll have to cut down on questions now. There are many more with that I can see. Maybe Tarun, maybe Dheeraj can will you like to provide some outlook? Talk to Vijay, thank us.
Yeah, great talk, Vijay. I'm really, and when I saw some of your slides, and particularly when I saw this transformer architecture, I read that paper just 2 days ago.
Wow.
I was at IIIT Delhi and I was meeting with this guy who works on LLMs. And I said, look, I'm a networking guy. I have no clue about how even these neural networks operate. And please tell me, how does this NLP thing works? So he talked about encoder, decoder, then attention, then transformer, and so on and so forth. So all that in your slides was really said, okay, just learned this 2 days ago. I think the biggest takeaway for me in this thing was these general methods being most effective. I mean, really, this was an amazing insight. How we think is not necessarily the way it will work in the long run. Absolutely amazing insight. And thanks, really wonderful talk. I think most of us who may not be in computer science, like I'm not in NLP or LLM and any of these kinds of areas, we could take away a lot of stuff, what's going on. And I hope we'll have other opportunities to invite you again. And at least next time you are in Jaipur, we will not miss that opportunity this time. We're sorry we couldn't organize that, but next time we should definitely see you on the campus with us. Thank you. Thank you very much.
Thank you so much.
And Vijay, just repeating what Dheeraj said, we would love it because today we only had our second semester students because there are examinations on. And next semester, whenever you can afford the time, it will really be a pleasure for all of us. Please do spend some time for us. Great.
Thank you so much.
Thank you once again to you and to everybody else who attended from different parts of the world. I can see some of Vijay's collaborators, etc., are also attending from New York, presumably, which is early morning. But that's okay. Okay. Thank you. Bye-bye.
Thank you, sir. Thank you. Thanks a lot.
Bye-bye.
Thank you. Taruna. Okay.
I think we should thank all the audience also. There was an awesome response by.
Yes. Well, sabko kaha na thank to everybody for coming.
And the talk was really very interesting.
Yeah, thank you for everybody for coming. I think we had a very good response, and
Sure.
thanks to everybody for attending this, please. Devika, सब